This is an explanation for the Munkres or Hungarian algorithm. This algorithm is meant to find a minimum matching between a table of costs. This can be used when there is a group of activities and each one of them must be performed by a different person, and you are trying to minimize the cost to complete each activity. To start the problem, first you need to create a table, like so. Let's say there are 4 people, Tim, James, Jess, and Alice, and they have 4 activities to do in 4 days. And the costs vary depending on the person who does it. And your job as a computer scientist is to find the minimal cost to do all of those jobs. To use the Hungarian algorithm, you need to follow 5 steps. First, you need to subtract the smallest entry in each row from all the entries of each row. Then subtract the smallest entry of each column from all the entries of each column, very similar to the last one. Then you need to draw a minimum number of lines so that all the zeros are covered. This can be done in different ways, but you need to use the minimum number of lines. If the number of lines is equal to the length of the matrix, then you have a solution using the zeros. If not, then you need to determine the smallest number not covered by any line, then subtract that number to all the uncovered numbers, and then add it to all the numbers which are covered twice. After doing this, you do the checking again, and if the checking fails, then you have to repeat this step until there is a solution. So here we have our table, and to start solving this problem, first we need to find the smallest number of each row. In the case of the first row, it would be a 5. In the case of the second row, it would be an 8, and then a 4 and a 4. So according to our pseudocode, first we need to subtract each minimum number from each row, getting this table right here. As we can see, we have already 4 zeros. Then we need to find the minimum number of each column, which are here. This is a 3, and the rest are zeros, because the zeros also count as the minimum numbers. Then you subtract it, and the only column that is going to change would be the first one. After doing that, you need to cover with the minimum number of lines the zeros. I managed to cover in this matrix the zeros with 3 lines. This line right here can go in this direction or in this direction, it really doesn't matter. And the number of lines that I found were 3, and in this square matrix is the size of 4. You need to do this comparison. As they're not the same, then we need to follow the next step, which is finding the minimum number in the uncovered numbers of the matrix, which in this case would be a 5. And we need to subtract it from all the numbers that are not covered, giving this result. After that, we need to then add that number 5 to the numbers that are covered with 2 lines, being a 12 and a 21, giving this result right here, this table. Then we need to proceed to cover again with the minimum number of lines as zeros. I managed to find in this case 4 lines. In here the same, this line could be going in this direction or in this direction right here. Now the number of lines is equal to the number of the square matrix, which this means that there is an optimal solution. So with the graph, with the zeros, we try to find a 0 in each line that doesn't overlap with the other zeros. We start with this 0 right here, then we cover. Then as this 0 is the only one in this line, we mark this one. As this line has 2 zeros, we cover this one. And the last line only has 1 0, which is this one. Then we go back to our original table, and in our original table we look at the numbers in the positions where the zeros were. We have an 8, a 13, a 4, and a 4, giving us a result of 21. That is the minimum outcome that you could get from this table. So Tim is gonna go with day 1, James is gonna go with day 3, Jess is gonna go with day 2, and Alice is gonna go with the day 4. The Munkres algorithm can be modified to find the maximum matching of a table. Let's look at it this way. We're gonna use the same values as we used before, but instead of having people doing jobs, we're going to have items that are going to be sold in a store. We're going to sell books, toys, sunscreen, and umbrellas in 4 days. These numbers inside the table is the profit for each item. We cannot use 2 items in the same day. So to modify this algorithm, first we need to think that we are actually not trying to find the maximum numbers. We're trying to minimize the loss of profit. So we're going to find the biggest number in each column, and then we're going to subtract it to the other numbers in the column. Getting the absolute value of all those numbers, we finish with this table right here. For that table, then we already have to minimize the losses because these numbers represent losses now, and we just need to run the algorithm. After running the algorithm, we get these positions, and to modify it to get the maximum profit, we just need to use those positions in the original table, getting these values right here, and after adding them we get 105 of profit, which is the maximum profit you can get selling those items in those 4 days. Now let's imagine that a new person called Tom is being considered to work in the team, but they still have 4 days. Well, the Munkres and Hungarian algorithms doesn't really cover this case like this. So to solve it, we just need to add a dummy column with the value of the biggest entry in our original matrix. This is because that column is not going to be considered unless that person adds too much value to the job. So to solve this problem, we just need to run the Hungarian algorithm in this matrix right here. Now let's look at the pseudocode again to find the time complexity. It can be said that it runs in omega of n cubed because it takes n times to go through the rows and columns minimizing them, then n times to find the minimum number of lines to cover the zeros, and then another n times to do the rest of the checking and the procedures to find the solution.